Let me continue. So this was the end result. If you look at this thing, just look at this and tell me what you see or what does it resemble. Well, let me help you. This resembles the left-hand side of a system of equations, the coefficients and the unknowns. It has n unknowns and m equations. Well, there's no right-hand side now, but this is like the left-hand side. Now, if I look at each column separately, I can see that this column is like this, the coefficients here are multiplied by x1. Then it's added to the second column times x2, the third column times x3, and so on, the nth column times xn. Now, this kind of combination, in fact, is called a linear combination of the columns of matrix A with coefficients x1, x2, xn. Okay, so this kind of structure is called a linear combination, and we will see why we call it linear, and our combination is definitely going to see that they are added together. So, and the coefficients means that okay, well, I can change the x's, right? First of all, if I had a right-hand side, then I had to find the x's, and sometimes x's are infinitely many, but the coefficients don't change. So these coefficients don't change when you solve a system of equations. Although, yeah, you make some changes to find the solution, but the system, the original system doesn't change. But anyway, so this, if I had a right-hand side, so if I had something like this, so let me erase this thing. If at the beginning I had something like this, A, and that x, let me put the vector here because that x was a vector, right? A column vector, equals a B, equals a B. So that is also a column vector. So if I write B here, so this should equal to B, which is B1, B2, up to Bn. Okay? So if this equals that, if two matrices are equal, then each entry here should equal to the corresponding entry here. This is entry 1, 1. So it should equal to this. This one should equal to this one, and so on. So in fact, what I have is a system of equations. If I write the equalities here, I have a system of equations. A11x1 plus A12x2 A1nxn equals B1, and up to the end, AM1x1 AMnxn equals Bm. So I have, in fact, I have a system of equations. So this Ax equals B, if I set it equal to B, then that is in fact a system of equations. So that whole system of equations, which is something like this, can be abbreviated or written as a matrix A, which is a matrix of coefficients, times matrix X, which is matrix of unknowns, and the B is the right-hand side. So A is coefficients for this. So this is a system of equations. System of equations with n unknowns and m equations. And A is a matrix of coefficients X is unknown vector, all vector of unknowns. Let's write it. Vector of unknowns. And the B, I would say right hand side. We will see in differential equations part of this course that that B is like a forcing function. However, when it is a function, it's like some kind of force which is applied to a system. So a system which is moving, for example, has the X will be the position of certain points in the system, and A is just some coefficients that come from the system, and they are fixed. A system has its own A, and then B is like forces applied to the system, and any force gives me a certain displacement. So let me erase this. But for now, it is basically as a system of equations that is a matrix of coefficients and vector of unknowns and right hand side, and that right hand side is a vector. So vector, just right hand side. Okay. So what do I have here? This is like saying x1 c1 plus x2 c2 xn cn equals b. Well, that's right. A vector on top of each one. So, and these are the c1, c2 up to. So each one of them. This is x1, c1, x2, c2, xn, cn is the last one, and equals b. So a system of equations, you can write it like that, ax equals b, or we can write it like this as a linear combination of some vectors, and that equals, say, b. Okay, so let me erase this, and I think I have everything. Well, not everything, so it's enough up to this point. We know enough to find matrix, multiply matrices. So let me see. There are two other structures that we discussed. One is the transpose. So if A is, say, Aij n by n, then A transpose is simply, right transpose on top, is simply Aj, which is n by m. So rows of this or columns of this, and vice versa. Columns of that, rows of that, or columns of this. So let me give you an example. So let's 1, 2, 3, 4, 5, 6, 7, 8, and 9, and 10. So this is a 5 by 2. Now, if I transpose this thing, I will get this. So this will become the first row here. 3, 4, 5, 6, 7, 8, 9, 10. Oops. These are too close. So. Okay, so transpose is simply write this as the first row, write this as the second row, third row, and so on. So that is transpose of a matrix, and you will see how important this transpose is. And another thing is trace. A trace of a square matrix. So if A is square n by n, then a trace of A is the sum of its diagonal entries. Right? So diagonal entries are diagonal entries. So trace of A, we write it TR, and sometimes trace simply. I prefer this one, but anyway. So this will be A11 plus A22 plus A33 up to AN. Okay. Well, this one is simple. Let me just write a simple example here for you. So let's find trace of this matrix. Trace of A, let's say 1, 2, 3, 4, 5, 6, 8, 9, 10. Well, I forgot 7, that's okay. Anyway, so trace of this is 1 plus 5 plus 10. So that's 15, 16. Well, I know I dropped 7, but that's the matrix. Okay, so it's that simple. So trace is just adding these entries in the diagonal. Okay. So I guess I'm done with matrices. Let me see if there's anything else. I can't see anything else here in this. Yeah. So well, let's start another section, and that section is in fact that's in fact inverse of a matrix. So this in the book is 1.4, I guess. So that's in fact 1.4 inverse of a matrix and some algebraic properties of a matrix. So in order to discuss inverse, we need to look at the set of matrices, square matrices of certain size in a different point of view, and that is this is an algebraic structure. But let me format, so I wish to use my lecture number 4 because I interrupted this. Okay, so well, let's take n by n, which is the set of matrices n by n with real entries. In fact, to discuss the algebraic properties, we don't need this. So let's m by n, a m by n with real entries again like this. Then if a, b, c are, so let a, comma b, comma c be in m by n, and this means so this means it belongs to. Some of you don't know, this means it belongs to. So that notation means belongs to. Okay. And do I need to, how many scalars do I need? And a, comma b, comma c are scalars, which means they're real numbers in our case. Doesn't have to be real, but real numbers. Then we have these, let me use my, I have written some notes here so I don't forget all of them. So I have a plus b equals b plus a. So it means that addition is commutative. Addition of matrices is commutative. B a plus b plus c is a plus plus B plus C. And then C, well, let me see which one is this. A plus minus, no. A, that's the scalar, plus minus B times C. It's like multiplying this A times C, and plus minus, you can expand this thing, distributes, and B times C, right? So, and what else do I have? C, D, so if I have A times B plus and minus C, then it also expands A, C, right? It distributes over this. And we see the other, is there anything else which has no. So these are the ones. Now this A can come here, right? So this can be B plus minus C times A. That's the same thing. A multiply on this side or on this side. But I usually write it here, but it's the same thing. Okay, now for the rest of them, I need A, B, and C to have a certain property. So not in A, M by N. So let's let me erase all these things and assume that they can be multiplied. So now they're not in M, N by N, they're not here, they're somewhere else. So A, B, C given. Now whatever I write here, the multiplications should be, should be well defined. So if I say A times B, I cannot multiply A times B if they both belong to A M by N, and the M and N are not equal. But over here, yeah, I can multiply anything by anything. In M N here is in M N by N, I can multiply anything by anything, but here no. If M is not equal to N, I can't do anything. But let's say that we have the multiplications are well defined. Suppose matrix multiplications are defined. So, okay, let's see what I have here regarding multiplication. So let's say A times B times C. It's like multiplying A by B, then by C. Then another one which has to do with multiplication is if I have A times B plus minus C, then this is AB plus minus AC, and BC, let's see. Okay, so if I have the other way around, A, then it is BA plus minus CA. One thing I didn't discuss, that is AB and BA. And what else do I have here? A, B, C, A, okay. So, and the D is if I have A times B, C, it's like saying A times B, then times C. And the last one, which is, did I miss anything? I don't think so. So the last one is this, in fact. A times BC is like writing AB, then C, or I can have B times AC. You see, the A is scalar, so either I multiply by B, then C, or I multiply B by C, then multiply by A, and so on. So each one of them is correct. I mean, they're the same, sorry. They are the same. So, these are properties, the previous ones were properties that I needed them to have the same size. These are, in fact, if they have the same size, if they are square matrices, then everything works. Otherwise, the multiplications should be defined, well defined. Now, I wanted to tell you something about BA and AB. So, matrix multiplication is not commutative. matrix multiplication is not commutative. i.e., which means that AB is not equal to BA. First of all, AB and BA can be multiplied if they have certain dimension. So let's say that example one. So let's say A is, say, 2 by 3 and B is 3 by 2. So when I can multiply, then this is like C, which is 2 by 2. If I reverse this thing, B 3 by 2 and A 2 by 3, this is another matrix. Why? Because it is 3 by 3. So if I reverse and the sizes are not the same, then this can't be equal to this. Can't be. Cannot be equal. Why? Different sizes. They have different sizes. But one might say, gee, what if they go 2 by 2? Does that work or it doesn't work for 2 by 2? Okay, let me check. And I'll give you an example of a 2 by 2. So, example of 2 by 2. AB, so that's 2 by 2. And this is also 2 by 2. Let's say, I guess every example should work. 1, 2, say minus 3, say 4, and then multiply by 5. Well, let me just write small numbers, so let me write something else here. Say 3 minus 2, 5, maybe say 8, something. So this is 1 times 3, that is 3 plus 10, that is 13. Then minus 2 minus 16, that is minus 18 here. This one minus 9 plus 20, 20 minus 9, that is 11 here. And this time this is 6 minus 28, no, 32. So that is minus 26. So this is AB. Then double check 3, 10, 13, minus 2, minus 16, minus 18, negative 9 plus 20, negative 9 plus 20, that is 11, then minus, that is plus 6, minus 32, that's minus 26. So, now let's go the other way. So that is B, A. Okay, let's multiply B by A. And 3, negative 2, 5, negative 8, times 1, 2, negative 3, 4. Minus, that's 3 plus 6, is it 3 plus 6, that's 9. Well, you can just say, I can just stop here, because this is not equal to this. Let's find all of them. So, 3 times 2 is 6, minus 8 is minus 2 here. Then 5 I have here, plus 24, that is 29 here. And 5, so put it up, and then I have 10 minus 32, and that's minus 22. So as you see, they are not the same. There's even not even one entry. So AB is not equal to BA. Now that might happen. You might get they might be equal in certain situations. So you might come up with an example that this happened. I'm not sure if that happened. Well, if you have like I times I, then you get I. So if you have two zero matrices, zero matrix times I, any matrix is zero. So either to the left or to the right, it is zero. So yeah, the special matrices that happen. So matrix multiplication is not commutative, and in any situation. Okay. Now, properties of a zero matrix. What is a zero matrix? A zero matrix, let's write it like this. So I distinguish it from this. So it's all zero. And by what are the properties of zero matrix? Properties of the zero matrix. Property A, if I add anything or subtract from zero, I will get A. B, if 0 is added to A, I will get A back. What else? C is if I multiply 0, the 0 number, by A, I will get 0 matrix. So this is number. Matrix. And D, I have A minus A is in fact A plus minus A is the 0 matrix. It's A plus minus A, so each entry is subtracted from itself. So, and there we see DE. And the last one is interesting. If I have a constant C times A equal to 0 matrix, then either C is 0 or A is the 0 matrix. This is 0 scalar, and that is 0 matrix. Okay, so this is interesting. Now, why? If I have scalar times matrix equals 0, that's true. Either this is 0, this is 0. It's not hard to prove. Just write down, just expand, and you will see it happens. But what happens if I have two matrices equal to 0? So let me give you an example of that, and maybe just stop for today. So, example. Well, let's write down 0, 1, 0, 2. Let's see if this happens. I'm not sure. 3, 4, 0, 0. So 0 times 3 is 0, 1 times 0 is plus 0. So this is 0. 0 times 4 is 0, 1 times 0 is 0. 0 times this is 0, 2 times 0 is 0. 0 times this 0, 2 times this 0. Okay, so these two are not 0. This is a non-zero matrix, and this is non-zero, but this is 0. Okay, so it doesn't happen in matrices. When you multiply two matrices and the result is 0, it doesn't mean that one of them should be 0. No way. Okay, so okay. I think it is good to stop now, and then next time I will define inverse and how to find inverse and other things. Okay, so let me stop now.